Greetings again. So this is our next video after I just completed my video for week 11. I'm going to talk about multiplication in this case, and we will also go through a number of circuits and ultimately settle with Wallace multipliers. Because of the length of this particular presentation, I'm going to divide this into two parts, and so in this first part I'm going to talk about primarily sequential multiplication and some in the front end of it some high-speed multiplication that's somewhat infeasible. And then once we finish that, we're going to look at some other techniques and also talk about sign multiplication all the way up to Wallace multipliers. So in this first half, as I said, I want to start out with the definition of what we consider multiplication is in the context of multiplying two n-bit numbers, which in this case are u and v. And u itself is an n-bit number, and v is an m-bit number, and we call the first operand u the multiplicand, and the second one v the multiplier. And when we talk about multiplying two numbers like u and v, as we said, we talk about just simply taking the binary representation of the multiplier, which this right-hand side is, and then multiplying it with the operand on the left, which also we can consider as a multiplication or as in a summation form as the right-hand side. But this initial expression is intended to focus on the multiplier bits and see how they actually impact the ultimate product. And of course, when you multiply an n-bit number by an m-bit number, you're expected to get an n plus m-bit product. So the size of the result is going to be the sum of the bits that each of the two operands contains. So the summation that we've written here, which represents v when multiplied with u, is equivalent to the summation on the right-hand side, where we just bring in this u into the inside the summation. And this really reveals it all here. All this is saying that this multiplication that we're referring to here is just a sum of the multiplicand shifted by an amount of 2 to the I to the left, that is multiplied by this quantity. These are the weighted values of the multiplicand. And then also keyed by these bits of v. If they were to be 0, for example, there would be no contribution of this particular term. But if this bit were to be 1, then it would make a contribution to the sum. So the v sub i's or the v bracket i's simply give us the capability to control the impact of the weighted multiplicand operand here on the ultimate sum. And of course, the v sub i's are randomly picked. This is just any number that happens to have m bits. And so in the end, this summation is just like this summation I've written down here in a sort of like a column form, where I've put each and every one of these terms in separate rows, and that way you get to see what really gets added. And of course, the u itself is a n-bit number, which we should not forget, because ultimately they'll decide the size of the product. So one way to think about this is, take each of these terms as they are and then put them side by side, like I've done here, and add them up. And add them up in a binary tree fashion, so that since there is a total of m terms here, if you can tell it by looking at the indices here, like 0, 1, and then all the way up to m minus 1. The width of this tree at the top is going to be m, so if you're just doing a binary reduction all the way down to the bottom, you're going to have a log m levels of computation, where m is the number of bits of in v, and the size of the addition, of course, is critical, as we'll see. And the way that so the binary tree level wise is a log m level computation, but each vertex itself needs to do something more than just simple OR or AND operation. It has to add its two operands together. So that, of course, is the addition problem that we looked at before. But in order to really sort of visualize this in a little more precise way, here I've actually taken all the product terms, if you like, these weighted expressions, and without really specifying what the V bracket i's are, and we don't know what they are, they could be 1 or 0. I've written these operands in the shifted form. So the first one, for example, this V0, 2 raised to 0 times u, is this expression here. And I just padded with m zeros on the left, so that's what the initial number is. And then the next one is like this term, which basically means that you got to shift this initial number, which is v1 times, or v bracket 1 times u, and that must be shifted by 1 bit to the left, and that's what happens. So in the end, you can kind of like keep shifting this. 2 raised to m minus 1 means like m minus 1 zeros must be padded on this side, and then everything gets shifted to the left. In this case, I'm kind of assuming that m is less than n, so that all the shifts would still keep it within this n range, because if in fact m were to be equal to n, we will just be right on the very boundary of this place, and then you would go n plus another n almost. But in this situation, m is less than or equal to n. I made that assumption here without making it too explicit, and so some u terms still remain within the range of the initial n bits here. So with that, you can see that this is just like addition of these operands. So the binary tree on the left simply takes those operands and then adds them up, and it overcomputes things because these zeros need not be added at all. But just to keep the complexity of the problem in perspective here, I've written this down. So the addition is really an n plus m bit addition then, because this is how they're extended. Each of these operands is n plus n bits. And therefore, you can just think of this whole process as log m levels of n plus m bit additions. And that kind of adder is what you need, which will be like a Brandt and Kung adder, in which case you will have log n plus m gate delay. That's what we just figured in the prior presentation video. And then you have to multiply it by log m. This is also at bit level because that's how we're advancing. And so that's the total gate delay. And that, of course, would be log square n if n were to be equal to m. Now, circuit complexity, again, if you just look back at this tree, the size of this, the width of this tree at the top is m, so that means the number of vertices here, the red circles, would be about order m. So now you have to multiply m by the complexity of each vertex. Complexity of each vertex will, of course, be that of a Brandt and Kung adder, and that will be m plus n, order terms. And so you have to multiply basically m minus 1 by n plus m. That's the number of red vertices, or the adders in the binary tree, and that's the number of gates. Again, if m were to be equal to n, then this will be order n squared. So now we know that there is a solution to the problem. If in fact we were to use the Brandt and Kung adders replace those red vertices by them, each of those, and then basically you have this sort of complexity, and that solves the problem in log square n time. Excuse me. So the question is, can we bring this time to log n and then maintain the complexity of the circuit complexity, perhaps not reduce it entirely to order n? Well, we're going to take a look at this problem in the second part of my presentation. But in this first part, we're going to basically now look at sequential ways of computing the same multiplication instead of like doing this in a binary tree fashion here. Excuse me. And so this is the fast way of doing things, as we just found that log square n time, but it requires a lot of hardware. Requires about m Brandt and Kung adders, each of which will have to add m plus n bits. And so this solution, excuse me, this solution is, I'm just still recovering from this call that I mentioned to you in my email, and it's slowly going away. Hopefully by Wednesday I should be all clear. But for right now, it seems like I've gotten one of these cough attacks. It's persisting, so hopefully it'll go away by itself. And this serial multiplication, it kind of like does away with that binary tree solution where we use only one n plus n bit adder right in the middle here, and we have our n plus n bit multiplicand. And then we have these partial products, which are these terms. Like if you look back here, we take these two, add them up, that's one partial product. And then we take that one and add it to the next one, that's another partial product. course, to be able to do this addition, we have to also add the shifted value of u. Every time we do this addition, u must be shifted by one place to the left, and that's what this diagram does basically. You take the multiplicand, which is m plus m bit sign extended. This is, these are odd-side numbers, so we pad them with zeros, and that gets added to this partial product, which sort of stays put in its place. So the shift left basically makes that alignment happen. And so now you're down to one adder, which is m plus m bit, could be Brandt and Kung. And now you have to iterate this. And of course, you're going to iterate this now for m bits. And this were to be an m plus n bit adder, which will have the complexity time-wise, gate delay-wise, log m plus n. And because you're going to do this m times, because you got m bits to do this with, the complexity now goes up to m times log m plus n, as opposed to log square n, or it was log m times log m plus n, which is this case that we talked about earlier. So the complexity, because we get to do this the same way, but this log m that came from the binary tree is now going to be m, because we're going to do this one bit at a time. This feedback process is just going to look at one bit at a time. So looking at one bit at a time just prolongs the time. It makes it go from this expression, which is log m times log n plus m, to m times log n plus m. This log applies to both these terms. So that's how it is. And then this is the actual circuit, not the actual circuit, but this is somewhat of a circuit diagram where the controller on the left is a long log m bit counter, which means it can count up from 0 to m minus 1, and that's the exact number of times we have to do this addition. And you've got the m plus n bit adder here. You got the partial product here, which is also m plus n bits. And then you have the H register, which contains the ultimately the multiplicand, which with padded zeros on the left. And so that gets shifted essentially to the left. You got the space created here. And of course, the product, the multiplier rather, is contained in the m-bit register here. And we get to take a look at the rightmost bit, and we just do this by shifting this by one bit to the right, which then makes this rightmost bit the current bit, which then gets added to inputted to this AND gate, which then gates the m plus n bit multiplicand into the adder. That's one of the two operands. The other, of course, operand is going to be this m plus n bit partial product, into which we are accumulating our final product. So the width of that is fixed to m plus n, so we don't really have any problems. So ultimately, all the terms will trickle into this space. So while we're shifting the multiplier to the right one bit, we're shifting the multiplicand by one bit to the left. Initially, of course, we copy the first n bits into this m plus n bit sign extended multiplicand from the original register of u. That's what that holds our multiplicand. Again, as I said, the counter here is just like simple looking to see if we reach the count of m minus 1. If we did, and that is to say, if this is greater than or equal to m, that means we reach the n. Then we're going to come down to here. That's going to basically make this output 0, and then when this becomes, then at that point in time, this becomes 1, and we end up computation. Otherwise, we keep going back to this as long as we're in this state, of course. So that's a simple loop that just counts through the process of shift and add, and that's your multiplier right there. And this multiplication circuit is going to take m times log m plus n gate delays, because that's the Brandt and Kung adder, I'm assuming. Other additions, of course, would make it go higher, because if you were to use, for example, a ripple adder, then the time complexity will go up to m squared, or m plus n times m, which will be actually order n squared. And so we're not using ripple addition, we're using Brandt and Kung addition. And so that's your serial multiplication, and this is just an algorithmic representation of the same. We're basically initializing the partial product to ui in the rightmost n-bit positions, and then the remaining bits from n on to m plus n minus 1, we're just padding them with zeros. And h0, the first iteration of the so-called the the multiplicand, this H register we talked about here, is also kind of like you load the n bits here and then you zero out the rest, but that has to be done for the 0 instance of it, because this is something that we keep changing. This is also true for partial product. So these partial product and H vectors will actually be updated here inside the loop as we run this K from 1 to m minus 1. Initially we set the 0 iteration position of both these vectors to the multiplicand. That, as you can see, that happens, and this really tracks the diagram. This kind of goes in here as the initial value. Now somehow I didn't put this arrow in there, but initially this has to also go here, which it does in this case here. And once you have that, then you have this m iterations, or m minus 1, actually exactly m iterations, because we go from 1 to m minus 1. And then you simply initialize the HK, which is now equal to 1 to 0, and you're going to update that by simply doing this shift. As you can see, that you're going to be shifting things from ith position to the I plus first position as you get to compute h of k from h of k minus 1, which will be 0. When you set this k equal to 1, that would of course be the initial set of bit values for h0. That's what this step does, and the same thing is happening to pp, the partial product bit vector. And so every time, of course, the sum that you compute is going to be greater or equal to 2, you have to do a mod computation down here, and then you have to generate the carry. So this is the simple addition portion of that whole computation, but you can see how these shifts are adjusted or affected by the value of k that runs from 1 to m minus 1 with k being initialized, or the h0 and p0, partial product 0 vectors. The 0 iterations, the first index of these vectors basically are just telling us that they are initialized to ui with some zeros padded on the left. That first index then is run from 1 to m minus 1 to get all the different iterations, finally the product, the ultimate product. So when k becomes m minus 1, this whole pp m minus 1 from 0 bit on all the way to m plus n minus 1 will have our product in it. That's the algorithm. So one way that we can simplify this is, instead of like using 2 times m plus n bits of register space, where that 2 m plus n comes from the fact that we really have these registers here, as you can see, 2 times m plus n, we can sort of reduce it to 2n plus n bits of register space, instead of by simply having an n-bit multiplicand, an n-bit partial product, and then using this n-bit multiplier register space to save the computed bits of the partial product. Basically what happens here is that the n plus m bit space that we have between the initial m bit partial product and the m bit multiplier is used to finally contain the n plus m bit product. And we just say goodbye to the rightmost bit. We actually get to use it once, and then after we use it, we never save it. So this was done in the early days of computer circuits, when companies that were in the business, and let me not even mention their names for disclaimer reasons as we talk about this in class. So whatever companies did this, were just trying to save some register space, because memory was the overriding concern at that time, 1970s, late 60s, and so on. So, but you can see that what this did, it just reduced the size of the adder from m plus n bits. That's good. You save some number of bits, especially if m is proportional to n. And also you reduce the total register space by just reducing this n-bit partial product, or n plus n-bit partial product to n-bit partial product. And then, of course, the multiplicand itself didn't have to be sign extended. And the way this works, of course, is you're going to be keeping this partial product in the same bit position. Well, I have to say it this way to be entirely correct. When you right shift this n-bit partial product, then the n-bit multiplicand kind of can stay put. Because right shifting the n-bit partial product kind of like ultimately it amounts to left shifting the n-bit multiplicand, because you're just simply dividing this partial product by 2 by right shifting it by 1 bit to the right, and that means you're doubling the value of n-bit multiplicand by shifting it to the left. So if you shifted it to the left, you would multiply it by 2, but you're not. As you can see, that you're just taking it as it is. So in order to be able to create that effect of multiplying this n-bit multiplicand by 2, you're simply right shifting the n-bit partial product by 1 bit to the right. The net effect is that the n-bit multiplicand is magnified by a factor of 2 before it gets added. So this is done every cycle, every one of the cycles in the iterations of the multiplication, and that's how this whole thing works. So here's the circuit, corresponding circuit, and so you can see that you have an n-bit multiplicand, n-bit partial product, and this is right shifted. And then this right shift, the rightmost bit of the partial product goes into the multiplier. And then the bit on the right of the multiplier, the rightmost bit, is used to control this process. Basically, the control circuit is exactly the one that we used earlier. And so this n-bit 2's complement adder is something that is used to add in this case, but it could also be used for subtraction if there were to be any corrections made to the result. But in this case, we're just simply adding. And so this is how it works. I mean, the same structure. The control is on the right-hand side. It was on the left here in this diagram. So that same control kind of works the same way. There's nothing really that's changed in that regard, because we're still doing this m-cycle computation, which still goes on in here. But I didn't show the entire circuit here. Just looking at that rightmost bit, which decides whether we should actually add the amount, the n-bit multiplicand, or we should just simply shift. So this is the control is just going through the motions of this multiplication, just looking at this, whether we actually get to add or not. And we could just be adding 0 here. Let me just take it back. Okay. I mean, there's nothing that is different from this circuit that we did earlier. Just the same thing. We're just adding all the time, and this 1 bit was coming in and ended, and so you could even have a bank of zeros, or whatever the extended multiplicand would be reflected in here. The same computation happens here. This n-bit multiplicand kind of controls the process. You could either add or you don't really add the term. I didn't put the gate here, but it is. You can assume that it's kind of there. All right, so this, I think, table explains, why is it that shifting p the same as like shifting p to the right is the same as like shifting the multiplicand to the left. You can kind of see that happening. This is where the multiplicand is shifted to the left, and of course here we took the multiplier here and shifted by 1 place to the right, where we didn't shift the original multiplicand. You can see that would have been here, so you can see that the same bit patterns, the bit pairs are added. P6, P5, P6, P5. So this is obtained by shifting U to the left. U was originally here, and in this case, P6 is shifted by 1 bit to the right in the second case, which is like what we're doing in this case, shifting the partial product to the right, and that's what the second option is. And you can say in both cases, the pairs are the same pairs. So effectively, the same computation is obtained. Now here's an example of the serial multiplication where we're multiplying 4 by 13. Our multiplier is actually 13, as you can see. And so in this multiplication, we have the partial product initially clear to 0. And we're looking at the rightmost bit, which in this case is 1, so we get to add a 4, and that's what happens. And so this is the sum. Now comes the shift time, or the first shift process, and we're shifting partial product to the right. There's no multiplicand shift here. And when we shift, we insert a 0 on the left, and that simply shifts everything by 1 bit to the right. And of course the 0 bit that used to be here is now moved down to here, and the bit that was here is destroyed. So these 3 bits have been shifted to these positions, and that 0 that was here has come down to here, and that 0 is padded on the left. Now second bit that we're looking at, this is the pivotal bit here, is 0, so that means we're going to add 0. This, of course, you can also avoid doing this addition, just simply bypass the circuit, but the path is there, so you're not going to be able to actually bypass it. The adder is there. So you're adding effectively. So you add. And now you add the two together, you get this result. Now you have to shift by 1 place, and that means this 0 comes into here, and that 0 goes out, and then these two ones travel here. And then the 0 comes in, and these guys go down here, and then so you have 0, 0, 1, which is what these are. And then you get the next place. Now you have to add the actual term, because the rightmost bit at this point in time is 1. That means you have to copy 4 down here, which you do. And then you take that 1, that 4, and then add it to whatever you got here. And you add it just like normally you would add it. And then you get 0, 1, 0, 1. And that thing now has to be shifted by 1 place to the right, which you do by bringing this 1 down here. Of course, the 1 over here, that 1 is gone. This 1 is going to travel here. And then, of course, 1 goes down here. And then 0 and 0. So those are the red bits. So we're actually computing the partial product by these red bits, if you can follow. And so this whole thing continues. The 0 comes in. And then one more time, and we have to add this 0, 1, 0, 0. That is this 4, because the bit is 1. And we do. And then after that, we have to shift again. So by the time we shift, 4 bits that we computed for the partial product are shifted to the right. And then the other bits remain as they would be as the higher order 4 bits of this product. And that's what the result ought to be. So here's your 4, that's your 16, that's 20, and that's your 32. So it's 52, and that's what it should be like. 4 times 13 is like 52, which this number represents. So that's how you multiply with this multiplication circuit, where the size of the operands for the the addition circuit here is kept to n bits, not m plus n bits, which this circuit was. And this is obviously more expensive. Not only that, we also had these more expensive registers in terms of the number of flip-flops that we would need inside those. And so we've just made some gains in there, and this example kind of illustrates why this really works. It's an example. Of course, it doesn't prove it, but you could kind of follow this. So so I think maybe we're at a point where I may want to take a little break, but let me see if this will be a good place to break. I'm looking at my time. I don't know how much time I really spent on this, but if I go down a little bit, I think I'm coming down to recording basically. So maybe I will just cover this a little bit, and then I'll stop at the end of this. I haven't quite timed myself in terms of how much time I'm going to spend on this. Let me look. I want to split this right in the middle so that the second part has some. Okay, so let's just go through this also. So in this speeding process, okay, so let me just back up a little bit, and then we can talk about this. So that was the example which we just completed. So speeding up multiplication here really refers to these sort of unnecessary additions of the multiplicand to the partial multiplier when we have to have, or when we were to have, or if we were to have 0 bits in the multiplier. Basically, those additions are not needed because adding 0 to an operand or to a partial product doesn't really change it, so we should not really be doing that computation. So that's one thing. Now, the other thing, of course, is that you have these ones. Ones kind of behave symmetrically to zeros. And so if you have a bunch of ones sort of like a bundle together in your multiplier, these are the bits in your multiplier, you can also create some mechanisms by which you can actually reduce the number of additions essentially to 2. So that's what recording is all about. But before we do this, let's just look at the number of 1 bits that we might actually have in an arbitrary or randomly drawn a multiplier. So if we toss a fair coin to make each bit in a multiplier, n-bit multiplier, a 0 or 1, then the total number of patterns will be 2 to the m, and I of those will be 1. This is the probability. We want I of those bits to be 1. This is the number of positions, m choose I positions. We want those positions to be 1, the other positions to be 0. This is like the probability of that. And so you can say that the average number of 1s would be then the probability times the number of 1s, which then this sum is. And if you really do this, carry out the summation, you're going to get basically m times 2 to the m minus 1 divided by 2 to the m. You can take this outside the summation, and this you can really prove by binomial theorem rather easily. But in the end, you can see that this is going to come out to m over 2, which is what probably you would have expected, because half the numbers would be, half the bits would be 0, the other half would be, on the average, would be 1, zeros and 1s. That's how they would be distributed. There's nothing really fundamental about this result, which is something that we should have expected. So on the average, you have that many 1s, and if they also bundle together, they kind of like come together as consecutive sequences of 1s, we could actually save some of our additions. So the idea is this: whenever you see a substring of 1s in the multiplier operand, all you have to do is to replace them by a string that begins with a 1 and a whole bunch of zeros, and then followed by a minus 1. To make this more specific, if I were to have 1, 0, 1, 1, 1, I would replace it by 1, 0, 0, minus 1. And you can see this equivalence between the two, that this number is really nothing but 7, and so is this number. So this is like, minus 1, there's a minus 1 in there, times 1. This is 2, this is 4, this is 8, so 8 minus 1 is equal to 7. So what this does, it replaces 3 1s by a 1 and a minus 1. But if you were to have 4 1s together, now you get 1, 0, 0, 0, minus 1. You still use 2 non-zero entries, 1 and minus 1, and you have 4 1s replaced by that. That means you actually have gotten yourself savings of 2 multiplications, because 2 of the 4 1 bits disappeared in this representation. This is called a signed digit representation, where minus 1 really is going to be ultimately represented by like 1 underscore. And so more and more of these would be generated by longer and longer strings of 1s. And ultimately, they'll save you the time. So here's like 15 times 9, which is equal to 135. And that 15 is written this way, times 9, which is actually equal to 16 times 9, which is what this 1 bit does to 9, and then the negative term comes from the last one, which is like minus 9, which is equal to 135 also. So algebraically they are identical, so but this, in a higher level of thinking, maybe you could say that you could attain this product 15 times 9 as basically 16 times 9 minus 9, which is obviously the case. What this equation in the binary level does, it saves us the number of steps we have to execute, because 16 is a better number to deal with than 15. 15 has got all the 1s, 16 has just one in there, but now we have to deal with the fact that we have to make it equal to 15, so that means we have to subtract as opposed to add, and that's where this minus 1 comes from. So that's what this recording multiplication is all about. With that, we now want to be able to do this in a more mechanical way, and that's called recording, as I said, and we'll just gradually gets us to this Booth multiplication process. And we want to know where the negative 1s and the 1s will have to be inserted. So the way to look at this is that we have to have the current bit combined with what we call the recorded carry in bit, which will come from the right hand side, And the two together will tell us exactly what we should do. So if we were to have a current bit, which we're trying to recode, whether we want to make it a -1 or a 1 or keep it as 0, along with another bit that's coming in, which tells us somewhere along the past part of this string, some recoding may have been done. And 0 means that no unbalanced so-called recoding is left at this point. And you have a 0, you don't really start a new recoding. So that means you're going to recode the bit as 0, no change, and then the recoded carryout will be 0, meaning that you have not done any new recoding. And so that's going to correspond to what we call shift. Basically, what a 0 does is a shift. And if you were to have a recoded carry in, and the new bit, the current bit you're looking at is 0, that means you've done some recoding, but that has not been terminated. So the recoding, of course, does place a -1. When you first started recoding, like, let's say that we start out here, we start out by putting a -1 in there. Now that we've made that recoding, somewhere down the path, or up the path, we're going to have to find a place where this 1 can be placed in. So in this situation, you skipped over the next one, which this position is, and then the next one, which this position is, and then finally place the 1 after the 2 1s. That's where we found the place to make this 1 in there so that the impact of this -1 can be actually replaced. Because by placing this -1 in there and then zeroing out all the terms in between, we're making this number much smaller than what it was initially, but to compensate for that, we have to put a 1 in there, which is basically algebraically what we explain here. So, but the critical thing is to think about when the recoding began, and if that recoding was ever actually compensated at some point. That would be indicated by the recoding carry being equal to 0. If it isn't compensated, as in this sort of case, then you really have to place that matching recoding bit of 1, which is what we do in this case, into that position where you found a 0. So you found a 0, and the incoming recoded carry-in was 1. That means some unbalanced -1 was created. Now you have to make it equal to 1 so that they get balanced together. And if the current bit is 1 and then recorded carry-in that comes in as 0, that means you have the opportunity now to start a brand new recoding, which is what this one is standing for. And so recorded carryout would be 1. And of course this will have to be now -1. This is like the first place you're starting your recoding. As we did in this example or in that example, in every one of these cases, we start out with a -1, which this under bar 1 is. You may not be able to see this. There is a little bar underneath this one. That's actually a -1. Instead of writing -1 here, I'm just using this notation so that it's sort of symbolically, denoting a -1, but only with a single digit. And that will correspond to subtraction, basically. And of course, you could ultimately encode this as a pair of bits, like with the current bit and then the recorded carry-in bit being 1, 0, would just amount to this being a recorded bit of -1. Final case is when the current bit is 1 and then the recorded carry is also 1. This is like here, like you're here. There is an incoming recorded carry of 1, but you're right there or even there. And you also have a current bit of 1, which simply means that you really have to continue the process, and therefore you really have to place, as we did over here, a 0 in the recorded bit position, as you can see it here in every one of these cases. And of course you must generate a recorded carry out or carry bit of 1, which we do here. And this will also amount to shift. It's like symmetrical to 0, because ultimately you put a 0 in there. Every one of these 1s in between, except this rightmost one, which is replaced by -1, would be replaced by 0. That means shift to the left. So that's what this whole process is about, and this really gives us a tabular way of taking an input sequence and then generating, and I've explained these, so I'm going to pass on this particular description here. As you can see, I talk about the runs of 1s and why we put the -1, why now we're putting the 1, and so on. So I'm going to leave this out. But this is an actual sequence, So we begin on the right hand side by assuming that the recorded carry itself is equal to 0. So this comes in as our first bit, and now we are looking at 0 as our recorded carry, n of 0, and there's a 1 in there, which is our binary sequence. These are the carries that we generate along the way. So 0 and 1 combination would actually start us out with a -1, which we do. And of course we'll generate a recorded carry of 1, which this is at this point. And now we have 1 and 1. That means we have to record this as 0, but you have to generate a recorded carry of 1, which we do. And we keep doing this for the next round. And we still have to generate a recorded carry of 1, but now we have a situation where we found a 0. And that means this is where we terminate this 1 by placing it down here. So we really have now paired the -1 with this 0 position. That you can see that's how that lined up. 0 was converted to 1. So now we start a new one, as you can see, and that only goes for a length of 1, and then the pairing 1 comes into this position. This one and this one, they pair up. This 0, 1, 1. You could kind of look at this. 0, 1, 1, 1 is what this is. 0, 1, 1 is what this is, and then you have 0, 1, 1, 1 again, which is equal to this, and that 0 remains put. And that's obviously how you would like to think about it. You have these chunks of ones that are stuck between zeros, and then the chunks of ones are just followed by one of the zeros that we talked about here. This is a 0 followed by a chunk of ones, then converted into this 1, 0, 0, 0, and a -1 pattern. And so effectively, the recorded sequence is sort of generated by this process. The other thing that you have to maybe watch here is that the binary sequence that we have here has something to do with the recording carries at the top. If you look carefully, the recorded carries are exactly like the binary sequence itself, except it's been shifted by 1 bit to the left. You can see that we put the 0 here, and then the 3 ones have been copied to the left. A 0 is copied here, 1, 1, 0, and then triple ones, and then 0. So that shifting kind of is something that tells you that you could actually take the binary sequence itself and then shift it by 1 bit to the left, and that's how you compute the recorded sequence. That sort of makes it somewhat more straightforward. And so, as I said, it just suffices to examine the consecutive bits of the original binary string, current bit to previous bit, and then it tells you exactly what to do. So we just did away with, I guess, the recorded carry in and carry out bits. We're just looking at the previous bit of the string that we want to recode, and it gives us the ability to actually compute the recorded bit. And that's all we want, just to generate the recorded bit to do this computation. We avoid just having these separate carries in the process. One problem with this is, as I'm actually sort of pointing out here, is that when you have some very peculiar sequences, one of which is really this, you will not get any benefit. In fact, this will just cause you problems. Like if you start out with this, you put a -1 in there, and there's a 0. That means you have to terminate it. You have to put a +1. A -1 and a +1. So in other words, all the zeros in this sequence will be converted to 1. So you start out with about as many ones as you have zeros, so half zeros and half ones. Half the total strength was kind of like half zeros and half ones. But now, at the end of the recording, it'll convert itself into only ones and -1s. And that means you basically double your effort of sort of like simplifying your multiplication. If we're still concerned about our multiplier being the sort of representation of our bits to determine whether we should multiply or shift, it's just telling us that by this sort of a sequence, we're not doing any better. We're actually doing worse, because we make the zeros turn into ones, and then the ones become -1. So -1, 1, -1, 1, -1, 1, and that's not going to help us at all. So one way to avoid this is actually have a bit of a look ahead. In other words, before we commit ourselves to make this conversion, to make this into -1, if we looked one bit ahead, to the left that is, we could see that a 0 is coming, and then we'll just simply not convert this into -1. And this should be okay as an algorithm in and of itself, because if we were to have two ones, in the worst case, when we have these two ones, consecutive ones together, we're going to replace the pair of ones by -1 and a 1. And that means that we really haven't gained anything, but we haven't also made it more complex. And so that is useful to know, because we could apply this algorithm uniformly. And sometimes we're going to have 3 ones, 4 ones in a row. But wherever we had 2 ones, we will just break even. When we have less than 2 ones, we will not commit to conversion, and therefore we will not really add any extra bits to the number of 1 bits we add. So we will have basically no more. In the worst case, if everything's like 2 ones and a 0, 2 ones and a 0, will come out to be exactly the same number of ones as we had in the original string, except some of the ones will be -1s and the other ones will be just ones as before. Okay, so so that's this table accomplishes, and now we're looking at the next bit, sort of to decide that we should really not convert. So if the next bit is 0, current bit is 0, and the recorded carry in is 0, then this is like, we don't have to worry about anything, because we don't have to. There's nothing coming in. The current bit being 0 without having any recorded carry in means that we have to be in a quiet state, so nothing is recorded. Carry out is 0. Carry recorded bit itself is 0, so that's just a shift. If it's 0, 0, and 1, this is where we would not commit ourselves to converting, because we have a 0, and this is as if we have this 1 bit coming into this position, and this ultimately is like a terminating recorded carry-in, and it is something that represents some recoding taking place prior to coming to this position. So it is not possible for us to actually move it over, because this bit itself is not equal to 1 to carry it over any further. So it has to be committed. That means we have to recode it as 1. But we're not generating any recorded carry out of 1, because we're kind of terminating this. This is kind of like how it was in the earlier table. Now here, this is another sort of case where we have a current bit of 1, but the next bit is 0. So this is where we kind of keep things identical. We would have originally, in the first algorithm, we would have actually recoded this as -1. But we're not doing it here. We just keep it as 1. And then we don't generate a recoded carry out, because we haven't recoded this. That's what this indicates. So this 1 with a 0 in front of it stays put. And the recorded carry of 0, of course, tells us that this should just not be recoded at all, because we only have 1, 1, and then a 0 leading. There's no recoding. And again, in the earlier algorithm, we would actually recoded this regardless of what the recorded carry-in would have been. Actually, if that were to be 0, we would have recoded this as a brand new sort of like recoding bit position with a -1. We're not doing that here, because there's a 0 in the next bit position, and this may complicate things for us, like this example would. So that's how this is, basically. Leave it as it is. And so in some ways, these two things are identical. You can see that they are the same, because this 1 could also be construed as like just a recoded, well, a current bit of 1 with a 0 in front of it. It should not be actually recorded, so we just put it as like a recorded bit of 1. That means we didn't put a -1 in there. Now here's an interesting case where we have a current bit of 1 and a recorded carry-in of 1. That means now we have 2 1s in a way together in this position, and that really corresponds to a shift, effectively, because 2 1s coming together tells us that we've had a recoding done before, and now we have a 1 in the current bit position. So this over here this must really be transported further, and that's what this means, recorded carry out of 1. And this, of course, bit must be turned off because now we have a 1 coming on top of it. That's what we did in the earlier algorithm also, so there's nothing that changes here. And of course, that means recorded bit of 0 is what has to be inserted in here. That's what basically this does. We recode it as a carry out, but the 2 1s basically seems that we have to put a 0. This is just the same as like in these examples where we have consecutive 1s, and then in which case like a 1 with a recorded carry of 1 would force this bit to 0. That's exactly what we're doing here, nothing different. So now we have these cases. Now we have the next bit equal to 1, the current bit equal to 0, and the recorded carry in is 0. This is no different than the first case. We're not really paying too much attention to this. This is sort of used as an auxiliary information, and we're more interested in what happens when the current bit is equal to 1. So in this case it's 0, nothing comes in. That's the same as like what we did before. Now here we have a different situation. We have a 1 over here, and a 1 is coming. So you can effectively think that you have a 1 and a 1. This 1 is going to sit right here because it's coming into it. So this is the same as like 1 1 0 case, if you like. And 1 1 0 case means that you really have to commit yourself to recoding with a negative 1 in this position. That is like a subtraction, which is what this negative 1 means. And of course you also have to generate a recorded bit of 1. So that's really the first place where you may want to think about this as having a 1, anticipated 1 coming on the left, and a 1 coming in, which makes this a 1 and 1 pattern. And a 1 and 1 pattern is commit to recoding pattern, and that's why the recoding with the negative 1 is what takes place. And of course you have to generate a recorded carry. And finally, not finally, but the second case, the next case, is exactly the same as this case, except the 0 is here and the 1 in there. So nothing is coming but the 2 bits that we want to recode. Current bit and the next bit, they both are 1. That means we really have to put a negative 1 in there. So these two cases are identical. And in the final case, you have a 1 and 1 coming. This must be recoded, regardless of what this is. That's what it is, basically. And that is going to be just a 0 recode and a 1 carry, because when this 1 comes in, that means something was recoded earlier, and now with a 1 in the current bit position, that can only be transported to the next place. In fact, this strengthens that. That means there's another 1 over which this has to be kind of like even recorded or transported over to the bit even beyond this. But these two positions containing 1, that is enough for us to actually record this as simply as a shift with a recorded carry out of 1. So that's how this table is created. And here's an example. This is a 0 carry, recording carry initial position. So we're looking at this, and this bit. So we have 1, 1, and 0. That means we really have to recode because we've got 2 1s in a row. Of course, when we do this, the recorded carry must also be 1. So we generate a 1, a negative 1 that is, that's recorded, and generate a carry of 1. Now that we generated this, we have actually 1 and 1 and 1. That means we have 2 bits coming into the position that the recording carry in is 1, but the bit itself is also 1. This is like where you have to put a 0 and you have to generate a recorded bit of 1. And the same is true here. Now you recorded you have a recording carry of 1 generated into this bit position, and this is what the earlier table was saying. The 1 will come in here, but there's a bit that follows it, and that's also 1. So that means you have 2 consecutive 1s. Now you have to commit a new recording of a -1, which is what this does. So when you look at these 3 bits right there, this triangle of bits, this makes it 1 because you got a 1 and a 1, like a 1. First thing that you may want to think about is to bring this 1 down here, so now you got 2 1s in a row. And that's when the negative 1 comes in. And of course that generates a carry of 1. Now these 2 bits 1, and that's in and of itself enough to make this equal to 0. So you kind of take this next carry out, recorded carry out becomes 1. And this continues. You get a 0, but a carry bit of 1. The same thing happens here, 1, 0, 1, and you put a -1 because the two together, like that one and this one, will generate this. So the whole process continues in this fashion, and then you have a recoded sequence which basically pairs the values together. And so this number is actually the same as this number. You can check it out by simply looking at the bit positions where the negative ones are like with the underbar ones. And you can see, in fact, kind of see that here because the one that appears here is one bit to the left of the highest most one bit here, so that you can say there's a doubling of this number here, but then there's some other ones in there, so it's not quite doubling it. And then these will have to be taken off in order to make this number equal to. But you can compute this to be 695 just to feel good about this conversion process. So I guess we did cover 2-bit recoding. And this next, I think, discussion is going to be about recoding with a higher radix. And so the higher radix recoding is something that comes out of the need that you can actually compute more bits together to sort of speed up your computation. And in order to do this, you can kind of group bits together and then think of this as a higher radix computation. So for example, when you take a look at this number 14, you can think of that as 1, 1, and 1, 0. So now you can decide how you're going to recode these numbers, you know, as like this being 3, this being obviously 2, and you can decide how to represent this. So basically all this is saying is that, you know, if you were to look at the product 12 times 14, one way to look at this is just simply say, you know, in radix 4, this is just equal to 12 times 3 times 2 square, and then 12 times 2 times 2 to the 0. So you can see that 3 comes from here, and then the 2 comes from there. And the exponents of the term here is like 2, 0, which is really 4 to the 0, and this is 4 to the 1. This is how this representation is. This is a basis for representation of our number, basically 14, which then gets decoded into these products. And so that to multiply 12 by 14 in radix 4 is basically doing this computation. This is a radix 4 digit, which is 3. That's a legit digit in radix 4, and so is this one. In binary, they would not have been, but our base has now been shifted from 2 to 4. So this process is important because whenever we take these bits together, we can actually look at their recoding, and their recoding, of course, will follow similar patterns, except that now because we have partitioned our, let's say, multiplier into blocks of bits, we can actually run them in parallel, and also we can compute these amounts of shifts quicker. So this could be done for any radix, and this shows, in fact, how we can do this in radix 16. And you know, effectively, what we're doing here is we're taking some number like this, and then we write this as basically D, and then 9, and then 7, and then 9 again. These are the basically hexadecimal digits that we express it in. So this gives us the capability again to just deal with these 4 bits of blocks of 4 bits in the recoding process. And of course we need to find some way of recoding, and now that we've compressed the representation, reduced it basically from let's say, you know, 4 plus 4 plus 4, 16-bit of a number down to basically 4 hexadecimal digits. And if we could just take these hexadecimal digits and find a quick way of recoding them, we can finish this whole computation basically in 4 additions as opposed to 16 additions. And that's the whole idea of recoding with a higher radix. So here's an example, I guess. We can have this particular sort of pattern converted by using 1-bit recoding into this, assume that this is correct. Now, what you can do is you can then take them as, pair them up, pair them together, and when you do, you get -1, you get -2, you get 0, you get -1, you get -1, you get basically 1. That's what this is. So instead of having, I guess, 2, 4, 6, 8, 10, 12 bits, you're down to 1, 2, 3, 4, 5, 6 bits. So you cut it in half, basically. And so this is effectively a way to deal with fewer additions, if you like. And the idea is this, that if you look at these numbers that we generated, these are basically all power of 2 numbers. Like -1, you can write this as -2 to the 0, -2, you can write it as -2 to the 1. 0, of course, is 0 itself, and then -1 the same way, 0 times 2 to the 0. And so every one of these numbers is some power of 2. And that's useful because when we have a power of 2 digit, if you like, in binary, that means we're going to shift it by that power of 2. If it's like 2 square, we shift it 2 times. If it's 2 cubed, we shift it 3 times. So it only involves shifts. So these digits being just powers of 2 is useful to have, and that's what's really happened in this example. And so anything that we want to multiply with this sort of multiplier, operand, which would be the original sequence here, can now be basically done by this process. As you can see, you have the operand u multiplied by effectively powers of 4, because we have digits that range between -2 and +2, and that means we have our radix set to 4 with a negative, of course, 2 included in the representation. So we really have -0, +0, -1, +1, and we have 0. And that's a notation we have. And so you can see where the -1 would come in, and that would be like for this. And then there would be another -1, that would be for that. The first one was equal to 1, of course. And then you have 0, and that corresponds to this, and then -2 corresponding to this, and then -1 corresponding to this. So if you just really put the u equals 5 here, you can see that the result that you're going to generate out of this, I guess this is written in the reverse order here. It's like a -5, that's this term, and then -40, and then -320, and then -1280, and then there's one of them is 0. I guess one of these terms must be, this is the one that is 0, and then these terms are there, both negative terms, and then finally this term. So that gives you this 3,475, and then you have with this one, of course, if you just multiply 5 by 695, you will get 3,475 as well. Of course, the idea is that we have reduced the number of operations ultimately from, let's say, 12. I guess this was the count that I had, 12 bits, to 12 rounds of shifts and add, or subtracts if you like, because there are some subtractions in here, to only 6 such steps, from 12 to 6. So that we were able to cut it down in half, only because these bits turned out to be -1, +1, and -2. There's no +2 in this case, or 0. That simply means that we could just simply do with shifts. No more than shifts is required to perform this computation. Effectively, if you just do 3 bits at a time, for example, you can get a radix 8 representation. And again, looking back at this bit pattern, if you just take them 3 at a time, that would be -1, -1, and then -5, and then a +2, which is basically what this is: 2, -5, -1, -1 again. And then you can just do the same computation, which then gives you the same value that we computed before. So The problem, of course, in this case is that we got this -5. That's not desirable. That's not a power of 2, and that goes to tell us that we cannot do this arbitrarily, because what we want by the time we finish this conversion, that all these terms to be powers of 2 with a negative or a plus sign in front of it. Only in that case, these higher radix digits will actually be useful. If you have -5 here, that means you have to shift 4 times, and then you have to shift once, or just not shift one time. So you have to shift 4 times, and then of course that's like basically write -5 as -4 plus -1, and then perform the computation according to this. In other words, you have to do -4 times something, and then you have to add to that -1 times something. So the advantage of having higher radix sort of like dissipates very quickly as these digits become the non-powers of 2. So in this case, 5 is one such number. Everything else okay, but that 5 is going to complicate things. So this is where Wallace multiplication, I'm sorry, not Wallace, but Booth multiplication comes into the play. Let's see if I could actually get to this place very quickly. But let me just continue this a little bit more. I guess there's a lot more to cover here. What we can say at this point in time that we want to have in radix 4, for example, plus minus u, plus minus 2u, plus minus 3u terms. And only these terms. We want to have those, but nothing else. With the multiplicand available to us, we could actually compute these or pre-compute them before the multiplication begins. Of course, for each u, this could be different, these terms, but what makes them advantageous compared to the prior example where we had the -5, every one of these terms that we've written down here, except this one, can be done by simply shifting by one place or not shifting at all. This is again not very desirable. So basically we want these terms like 2 times u, 4 times u, 8 times u with a plus minus 1, with a plus minus in front of them. Things like 3 times u, 5 times u, 7 times u, they are not really as desirable, and they should be avoided at all cost. So we want to find a way to secure this. And the 1-bit recoding scheme that we actually used in the very first place allows us, when we group them into 2 consecutive bits, to create these digits in radix 4. Basically, it does this because of the fact that the algorithm that we just did, the first algorithm, does not permit 2 1s or 2 negative 1s in a row when the recoding is actually completed. It is something that is inherently built into the algorithm. And we could just consider, for example, these sequences. You can see that if I take, for example, this sequence, when I recode this, you can see what happens, that I will start with the -1, and I'll then put a 0 and a 0, and then put a 1 in here. And then I'll just simply look at the pattern after that. So, you get basically -1, 0, and then you will have a 0 and 0, a 0 and 1 rather, I'm sorry. So -1, 0, which will be basically just 1, and then this would be 0, this would be 1, that would be then equal to 2. And then this will, of course, would be 1 in and of itself. So this generally works for this sort of scheme because when you put a -1 in here, for example, if you start with the next bit position, you don't really look forward to what happens, what comes next. So either you have a 0 here or have a 1, and when you were to have a 1, then this will just start another recoding. But since you do this in pairs, you would really have only these terms, 0, plus minus 1, plus minus 2. And you will never get two negative ones or two plus ones, two plus ones or two negative ones. And that is basically because you terminate with a 1 and you start out with a negative 1. And that's kind of like what makes things, what keeps them separate. When you terminate with a 1, you start with a negative 1. And when you start with a negative 1, you never put a 1 after that. You have to have a 0 following that. That's how the algorithm kind of works itself. So with that, we could say that this algorithm will just work properly, and just compute these bits in a way that the digits will be basically powers of 2, like plus minus 2u or plus minus u or 0. So that's I think sort of like inherently built into the algorithm, and that makes things rather pleasant for this particular case. So let's see if I could continue with more of this stuff. Just checking to see exactly what else I have to cover here. The same result really not necessarily, I think, valid for the 2-bit recoding scheme. Or is it just the other way around? I'm actually checking something here. Actually, even for the 2-bit recoding scheme that we covered, this also applies, is what I just concluded here. And that's because, again, we are not able to bring these consecutive ones together or negative ones together. So if you look at this pattern, for example, you can see that in the end you have converted this into this pattern, which is equal to 0, -1, -1, and 1. So I guess we could possibly do some examples of this in class to clarify this further, but I'm just going to move on to the next slide and to see if I could talk about Booth multiplication. Now, here I think I'm referring to how to generate these basically plus minus 1, plus minus 2 digits. And in the case of the single bit recoding that we did, we can simply look at these patterns in pairs, because if you remember, we were just generating these recoded bits by looking at the previous bit and the next bit, so we can kind of do those things by checking the pairs. And so that basically gives us like 0, 1, 1, 1, and then 1, 0, and then 0, 1, and then 1, 1, and then there's a recoding bit of incoming bit of 0. That's where the 1, 0 comes from. So this sequence is basically computed by having these pairs from which we can then generate directly the 1 and then all the other patterns that follow. How this gets recorded into basically this representation. So you get basically -1, and then this becomes 2 minus 1, which is equal to -1 minus 1, that's equal to -1 plus 1, that's equal to -1, and this is equal to, so this becomes like 2, and then -1, and then -1. That's how you get to basically generate this. But these can be computed directly by pairing these, and then I'm just looking at the representation of these in 2 bits. In basically radix 4 with 2 plus minus 2, and then plus minus 1 and 0 as being the digits. So the next algorithm, which is really something that I wanted to talk about, is the Booth recoding algorithm, which ensures this property that I just mentioned, that you will get nothing but 0, 1, -1, 2, or -2 as a result of this recoding. And what Booth algorithm does, it actually looks at 3 bits at a time. As you can see, these are the multiplier bits. and then generates 2 bits at a time. I'll just take a look at the example of this on the next slide. And so what happens is that these bits are computed based on, of course, the values of these 3 bits. But there's really a formula for this, and the formula is written down here. Let me just get down to the formula right away. It is really like um, the leftmost bit and then the bit next to it added, and then the rightmost bit basically multiplied by 2 and subtracted. So I guess there is a formula that I've written here somewhere. Okay. I haven't written it explicitly, but you can kind of compute this directly. So what we are saying is, if I take, for example, this is not a good example here, but if I take this, the way we compute this is we take this bit and this bit, add them up together, and then multiply this by 2, and then subtract that from the sum, which gives us the -1. So if you look at, I guess, this other representation, I'm sorry, I think we did do it the other way around. We actually multiply this by 2 and then subtract this from the sum of these 2 bits. The bits are in reverse order. So here we have it. So you have, in this situation, basically in this case -2 plus 0 plus 0. In this case -2 plus 0 plus 1. That's what is -1. And here it is basically, like I said, -2 times plus 0 plus 0. In this situation it's -2 plus 1 plus 1. That's equal to 0. That's what these numbers represent. So you really have these quantities, these 2-bit patterns generated directly out of the algebra that's shown in here. So these are not explicitly written, but you can kind of see how they get computed. Specifically, in this case, you get -2 here because this is like 2 times this bit, and then plus this and plus that. That gives you the -1. In this situation, you have -2 times 1 plus 0 plus 0, and that gives you the -2. And that's how you get to add these together. How you get to compute these bits together. So, of course, whatever values that you come up with, like here, if it's actually -1, that means subtract u. If it's -2, that means shift and subtract. If it's +2, shift and add. So you know exactly what you need to do when you see these representations. What is critical is that whatever you do out of this computation, you always get either 0 or 1 or a -1 or a +2 or a -2. No other multiples, I guess no other numbers. You could have had, for example, 3, you don't. You could have had -3, you don't. So the 3 does not ever appear in this recoding process. Of course, what we need to establish is that when we do this recoding, the recoded sequence is identical to the final sequence, or the original sequence, I'm sorry. So let's take a look at this. Now, here is how it goes, first of all. This is your original sequence, and you're going to look at 3 bits at a time, and you're going to generate 2 bits. So when you look at this, you are going to say -2 times this, which is -2, plus this plus this. So it's like -2 plus 1 plus 0, which is equal to -1. And these are your 2 bits that represent this. Now that you've done this, you move basically from these 3 to the next 3 here. So you can see that you kind of overlap by a bit. So you took these 3, but the next 3 you're going to take would be the bit at the leftmost bit of the first 3, and then the next 2 bits, because you're going to generate 2 bits at a time. That means you have to share this bit in order to have the number of bits generated in the same sort of order of complexity here. So you get 1, 1, 0, 0, 1, 1. Now you're looking at this, so 0 minus 0 plus 1 plus 1, that will be like 2, which is what this bit pattern is. This is +2. That came out of this, and you can see that they line up right there. And you take these bits, so it's minus 2 plus 1. That's actually minus 1 right there for those bits. And you shift by one place to the left. And then you take these 3 bits. Minus 2 plus 1. That's equal to minus 1. Take these 3 bits. Minus 2 plus 1. Again, that's like minus 2. Take these 3 bits together. Minus 0 plus 1. Plus 0 plus 1, that's equal to 1. That's what these 2 bits basically are. What these 2 bits are. I guess we're just computing this, then that must be these 2 bits, just like when we compute these 2 bits, I'm sorry. These 2 bits, because we always shifted by one position. So out of these 3 bits we computed this, and out of those 3 bits we computed this. So this 0, 1 comes out of the fact that 0, which is minus 2 times 0, which is still 0, and then plus 0 plus 1, that's equal to 1, which is what this is. And this is equal to negative 1 because you have minus 2 times minus 2 plus 0 plus 1, that's equal to negative 1. And so the rest are the same compute. Now, the thing that's really critical here is that the consecutive ones and consecutive negative ones never arise in this case. Again, those would be like negative 3 and negative plus 3. And there is a, this is sort of obvious from this, but why this is really, why the original sequence, which is this, is the same as this, is there's a proof of this by this expression. So let me just explain this briefly. What we're doing effectively is that we're taking these bits that are written as our the multiplier bits, V0 all the way up to, let's say, V m minus 1, if in fact we were to have m bit patterns, with a negative 1 index of V here just simply is referring to the bit that we add at the very beginning, that's 0, the red bit, which is always 0. So this V minus 1 is equal to 0. So now what we're doing is we're writing the original number, which was really nothing but V0 plus 2V1 plus 2 square V2 plus 2 cube V3. All those numbers is going to be written in this form. Now, if you look at this carefully, what you see here is that this being 0, so this is out of the equation. The only reason that's written in there is just to sort of show the format is maintained. So now you have V0 and minus 2 times V1, and you take that minus 2 times V1, and then you look at this representation, and you have 2 squared times V1, that's 4V1, minus 2V1, that means 2V1 in the end. And therefore you got this 2 times V1 term, which is what you wanted to have, which is really what this is right there. Now you look at the next term, V2 times 2 squared, okay, with a plus sign. And there's nothing else in here which would cancel that, so you keep it as it is. But V3, one of those digits in the bits in the odd position, is 2 cubed times V3, but with a minus sign. But right here, you have that same term, V3, multiplied by 16. So you had 8 times V3, 16 times V3, this with a plus sign, that with a negative sign. That means you have 8 times V3, which is what you have. So you can begin to see that this pattern, that you're finding this equation, this more complex looking expression, basically equating itself to our original V. Because we're taking the digits of V and then simply shifting them by powers of 2, and that's the original representation of V. I've taken it all the way to this place where I've written V3, but if you follow this again, you'll see V4 is going to be here with 2 to the 4, but V5 will have to be, with a negative sign, will have to be compensated with the next power of 2, and that's going to give you like the 16 times, 32 times V5, and that's going to continue. So there is a mathematical reason behind this, why this works. And that's because the two expressions are algebraically equivalent to one another. Excuse me. So I kind of leave it a little bit like as a exercise, I guess, at this point in time to see why why this encoding Booth algorithm will always generate. I've actually explained this. Excuse me. I kind of explained this earlier on because of the algebra of it, but here I just also dropped it as a question. So I think this more or less concludes my discussion of recorded multiplication. So let me just recap this. Effectively, what we did, we looked at a recoding process as an alternative to multiplying two numbers if in fact we were interested in reducing the number of runs of ones in the multiplier operand. And so runs of ones have been kind of like reduced in quantity, or they've been replaced by basically a pair of non-zero entries, one of which would be -1, the second one of which will be 1, and then in between we padded them with 0. So the more of these ones would appear together, the more savings we would have if in fact we could just shift faster without really doing the addition. This assumes that our data path has a way to shift things without really subjecting them to the addition. If the addition path is fast and the shift doesn't happen as fast, then the recoding algorithms will not be really as useful. May not be very practical. But if addition is slow and shifting is fast, then the shifting can be done in place without really using a addition cycle in the computation. With that, recoding makes sense. Without it, it really doesn't make as much sense, but nonetheless, we saw a way to take these ones and then turn them into zeros. If in fact zeros gave us a better way of dealing with the addition process that we have to deal with at some point in time when we are actually multiplying two numbers, because multiplication is successive addition. So I guess I'm going to basically wrap this presentation up. It's become somewhat long for me even, and but I think by and large I communicated most of the ideas of this portion of the course, and hopefully you'll view this video and then maybe generate some questions in class, and then we can discuss them further if in fact there's a need for this on Wednesday. So until then, take care, and I'll see you in class on Wednesday.